Yeah, it looks like I'm live. So yeah, um, so I'm gonna be finishing off the booklet today, trying to make up for my not great performance yesterday. To be honest, we were still solving at quite a fast rate because we did, excluding the last 30 minutes where I wasn't really doing much. We could do 102 questions in 3 hours, which is still quite a bit under question every 2 minutes. So we were still solving stuff quite quickly, but we didn't get close to finishing the entire booklet. So today I'm gonna be solving the remaining questions, which I wasn't able to do yesterday, which includes all of the graph sketching ones. So this could hopefully this doesn't take hopefully they're not that difficult. Yeah. So which one will we start with? Okay, let's do the integration ones. So okay, so 116. Um, this was the one like we pretty much knew how to do it. So yeah, like I think the method for these is like quite clear. So yeah, let's look at 117. So which of the following okay, yeah, which of the following numbers is bigger and why? Um, I'm thinking just I mean like x to the 7 is next to the 4 when x is between 0 and 1. So okay, maybe compare with like maybe say like t is x to the 28 and then compare in terms of t because you have the fourth root as well. So if we say t is x to the 28, then t to the 1 over 4 is x to the 7, and t to the 1 over 7 is x to the 4. So we have it's the 1 minus t to the 1 over 4 to the 1 over 4 for the first one, and the second one is t 1 minus t to the 1 over 7 to the 1 over 7. And then like this is a unique function, if that makes sense. So like t is between 0 and 1, and 1 minus t to the a. If I okay, as a increases, this function is as a increases, t to the a is gonna get closer to 0. So the function is gonna get closer to 1. But if a is small, then okay, so okay, if a is 1, then you have 1 minus t, which is less than 1. So it's but if you make a very big, it gets closer to 1. So as a gets bigger, this function gets bigger, and because 1 over 4 is bigger than 1 over 7, is it's the first one that's bigger. So okay, yeah, we did this one. Okay, hopefully we can do this quite quickly because yeah, I want to get some sleep. So okay, show that this integral is true. Um, it's the same thing. Like switch the do a u sub. So we do plug u as pi minus x. So du by dx is -1. So dx is minus du, and you have x is pi minus u, and you write in terms of u instead. So again, this is equal to from pi over 2 to 0, pi minus u, sine pi minus u, which is just u, over, I mean, 1 plus, like, the squared cancels it, so it's still cos squared u, because you get, well, you get, cos of pi minus u is minus cos of u, but when you square it, it's the same thing. Du, and you have a minus thing here, so yeah, we're done with the first bit. And then find that integral. Well, that integral is just, it's just this. It's just the sum of the two things, which we know are equal. Yeah, this shouldn't be too bad. Yeah, this should not be too bad. Um, oh wait. Okay, so it's the integral of. No, the integration is not my strong point. Um, yeah, so 0 to pi x sine x with 1 plus cos squared x dx is the integral from 0 to pi over 2 of x sine x 1 over cos squared x dx plus integral pi over 2 to pi x sine x over 1 plus cos squared x dx. And I can write this thing, or the first one, as in terms of this, which is pi sine x over 1 plus cos squared x minus this thing. And basically this is equal to the first one, which is this thing. So it's equal to this integral. And then I care about the sum, and the sum is equal to this integral. And you can just do this with a u substitute, put u as cos x, then du by dx is minus sine x, and then you have pi cos of pi over 2 is cos 90, which is 0, and cos 0 is 1, and you have sine x minus, okay, it's minus 1 over 1 plus u squared dx, which is the integral 0 to 1, 1 over 1 plus u squared du, and um, yeah, this is like tan formula. There's a formula for this, so yeah, we know how to do this. Okay, next thing. Show the show that this integral is true. Um, Probably put like x as sine theta. So dx by d theta is cos theta. So dx is d theta cos theta. And you know that 1 minus x squared square rooted is cos theta. So we have the integral is the integral from, okay, when x is 1, theta is 90 or like pi over 2, and when 0 is 0, so it's going to be sine squared theta over cos theta times cos theta d theta. So it's just the integral of sine squared theta d theta, which is this is easy to calculate because you can use the cos 2 theta formula because you have this thing. So you can get this integral in terms of cos 2 theta, and it's easy to integrate. And the other integral you can also get into a simple form, which is like you do the same trick. So for x is sine theta, then this is cos theta. So then you have dx is d theta cos theta. So you get it's 0 to pi over 2 of cos squared theta this time. And these two should be equal. Yeah, I think that's fine. Okay, and hence find this thing. Hence find it. Well, okay, I got a simple expression for it, so I know how to find it. What's the shortest distance? So, yeah, what's the shortest distance from point to the curve? Well, the point on that curve is of the form a squared plus 1, and you have 3, 1. So the distance is the square root of a minus 3 squared plus a squared squared, which is the square root of a to the 4 plus a squared minus 6a plus 9. And you wanna minimize this, so you wanna minimize the thing in the square root. So you wanna minimize a to the 4 plus a squared minus 6a plus 9. So you differentiate and set to 0. So you have 4a cubed plus 2a minus 6 is 0. So divide by 2. A equals 1 as a root, so a minus 1 um, minus 3 plus 2a here, I think. Yeah, okay, so the minimum is that a is 1. So you get 1 plus 1 minus 6 plus 9, which is like 5. Yeah, so the minimum is root 5. Okay, next thing. Short distance from y equals x to end that curve. Well, it should be like you have some curve and you have some line, so it should be a perpendicular, so this distance, and then this thing should be a tangent. So at some point on the curve, the gradient of the normal, the gradient of the tangent should be the gradient of the tangent should be 1. So okay, the derivative is 2x, so we want 2x to be 1. And that happens when x is a half. So at the point 1/2, 5 over 4, that's our point. And we want the distance between this and y equals x, which is kind of hard to get. But what we can do, we can say, okay, so we can find the point where it meets y equals x. So we can say like the the gradient of the line through this point with gradient minus 1 is gonna be this. And when it meets y equals x, you have x equals y, so we just need to find x. So you have x minus 5 over 4 is minus x plus a half. So you have 2x is 5 over 4 plus a half, which is 7 over 4. So x is 7 over 8, and then y is 7 over 8. So the distance is going to be like whatever this thing is, whatever the distance between those 2 points is. Yeah, that's the answer. And then shortest distance between those two curves. Well, it's symmetric in x equals y. So you have like two curves, something like this, and something like this. Um, do they intersect x equals y? Probably not. Because x squared minus x plus 1 doesn't have any roots because the discriminant is negative. So yeah, it has to be, the short distance has to be some sort of symmetric thing. So it's going to be like um the point on here is going to be like t squared plus 1, and the point of the other thing is going to be like t squared plus 1 and t. Because it's symmetric in y equals x is going to be something that's perpendicular to y equals x. Um, and you just do the same thing, you calculate the distance and you differentiate and you get the minimum. So yeah, that's done. Okay, the points, this thing are points on the triangle. The third point is on this. Find the coordinates of the third point, which minimizes the area of the triangle. Well, okay, so you have 6, 0. You have 4, 0, or 0 minus 4. And you have some point on this curve. Well, okay, let's say it's a squared. Then we can calculate, like, we can calculate the area of this thing. Yeah, so this is going to be 6. 4, so the area of this thing is going to be 12. This is a squared 6 minus a. Yes, we can get the area of this triangle, and then this is going to be a squared plus 4. So the area of this triangle is going to be 6 times a squared plus 4 minus 12 minus a half a squared 6 minus a minus a half a squared plus 4. And then like again you just differentiate, set to 0, find a, plug that back in, that's your minimum. So yeah, I feel like for a lot of these questions the methods are very clear, but the actual process is very long. And I think like it's not a very good use of time just to go through the method that you know how to do. It's more useful to like think about the thought process that leads to the method, and once you know what the method is, there's no point really executing it. I mean, for things like TMUA, it's all about executing it right, but like you can just get good at that by doing a bunch of practice, just by like spamming past papers. So I don't think there's any point of doing this live on the stream, but I think the main benefit is coming up with the ideas live, so you guys can see how someone else is coming up with the main ideas. So I'm sure that all of you watching this are good enough to like all of you guys are good enough to look at this, differentiate it, set to 0, and then find the minimum point. So yeah. Okay, next one. If I have a triangle of fixed area, fixed perimeter, what's the maximum area? Well, uh, Heron's formula is that if S is semi-perimeter, you have this, and S is fixed, so we want to minimize. We want to maximize this product where we can move A, B, and C. But A, B, and C have fixed sum. So okay, so by AMGM, okay, so fine. So S minus A, S minus B, S minus C have fixed sum because their sum is 3S minus 2S, which is S. So their sum is S. So by AMGM, S over 3 is greater than or equal to the cube root of like the product. So the product is at most S cubed over 27, which is like P over 2, whatever, over 27. And then, so what's the maximum error going to be? Well, equality occurs in the MGM if and only if A equals B equals C. So you put A is P over 3, B is P over 3, C is P over 3, and S is P over 2. So you get is the square root of P over 2 times 2 over 3P, and you cube this thing, and yeah, that's the answer. Does there exist a right angle triangle of fixed perimeter P with the smallest area? Okay, so you have A, B, C. This is 90, and your area is a half AB. Okay, but like surely I can just make B plus C equal to P, and then make A very small, no? Yeah, I can just put like B is a half P. Okay, no, I can put C as a half P, and I can make B tend to a half P, and I can make A tend to 0, so the area tends to 0, right? Like, if you imagine it, it's gonna be something like this, with a really small thing here, when these two sides are making up the perimeter. But I think, yeah, like you can make the area as small as you want if it's right. Okay, we did most of the ones. Okay, a gambler plays a game with his friend, and he bet half his money on the toss of a coin, won heads, lost on tails. Um, did he make money, lose money, or break even? Oh, lost as many times as he'd won. He'd lost as many times as he'd won, and he bet half his money. So I think he probably broke even. Yeah, I think he broke even because because the number of heads is equal to the number of tails, and he bets. Um, I mean, it's not clear how much he wins if he wins. Probably he gets his total money back. So if he has money M, he goes to 3/2M. So yeah, so if he wins his money times by 3/2, and if he loses his money times by half, and so if his money at the start was M, if he plays for if he gets N heads and N tails, and he'll have 3/2 to the N times half to the N. Which is 3 to the N over 4 to the N, which is less than 1, so he actually loses money. Okay. Yeah. Okay, 145. Alice and Bob play a game. Uh £1 a game. Okay, I'm guessing it's the same thing. So if like the winner gets £2, the loser loses £1. Oh no, no, the winner gets £1, the loser loses £1. Yeah. Um okay, so the sum is constant. Okay. So um okay. So okay, so the sum is constant. So all we care about is you need some sort of like induction type thing. Because if you look at the probability, okay, so for a given sum S, look at the probability of winning if you have K. Well, it's a 50% chance. So the expected value when you have K is half the expected value of K minus 1 plus half the expected value of K plus 1. Because, I mean, there's a half chance you go to K minus 1 and half chance you go to K plus 1. So, like the chance of winning, or like, yeah, we'll call it chance of winning with K, or say it's E of K. And yeah, so, okay, and if we know that E of A plus B is 1, because then you've won, and then E of 0 is 0. So, and we know that E of K plus 1 minus E of K equals E of K minus E of K minus 1 from this equation. So we know the thing is linear. So we know that E of A is A of A plus B. Okay. Next thing. Oh, this one. Yeah, I think this is kind of long. I'll skip this one. I'll come back to it. 150. Okay, so we figured out it's 11 beads in total, and you can have the colors be anything. And rotations are the same, but reflections are not. So rotations are considered the same. Can you rotate it and get the same thing? Well, okay, so let's say you have beads, some beads, 11 beads, and then you rotate it by k. So you've got a1 plus k, a2 plus k, like mod 11. and we're saying the A1 is A1 plus K, A2 is A2 plus K, and so on. Then what are we saying? So either like K is a multiple of 11, or like, or we had some block here equal to some block here. Yeah, I feel like, yeah, yeah, no, this is not possible because 11 is prime. Like, if it was 4, you can rotate it by 2. If you have, like, yeah, if you have by, if you have 4 b's, you can rotate it by 2 and get the same thing. But here, if you have a chain of length k and you rotate it and you get the same thing, that tells you that all of these were equal. So if I were to rotate it, if I were to do this rotation, um, a certain integer number of times, where the integer is less than 11, I'll get back to the original position. Does that make sense? Yeah, so we have to have k divides 11, which means that k has to be 11, or yeah. So, like, the only time you rotate and get the same thing is if they're all equal. So, I mean, it's basically okay. So it's really 3 to the 11. But you have some special cases. You have okay, rotations are considered the same. So 3 to the 11, um, minus 3, and for each one you have 11 rotations. Um, yeah, plus the plus 3 for the 3 where they're all the same color. So it's 1 over 11, 3 11 minus 3 plus 3. And this is an integer because by FLT, 3 to the 11 is equivalent to 3 1 11. Fine. Okay, what do we have left? We have this one. I'll come back to this at the end because I think this is like, yeah, I have no idea how to do that one. Um, well, we've done this one. We need to do this one. 108. Okay, we did this thing in the last video if you watched it. This one, um, I feel like yeah, let's not sketch it. Okay, yeah, I wasn't showing the right thing. Okay, I mean sketching these is like pretty easy. By integration, justify your claims. Oh yeah, we can use integration. So, oh yeah, so the infinite sum is going to be less than the integral from 1 to infinity of 1 of x squared dx, which is the integral from x to minus 2, so it's a minus x to the minus 1 from 1 to infinity, which is just going to be 1. So it's less than, wait, what? It can't be less than 1, well, yeah. Um, integrating 1 over x squared. Um, so minus x to the minus 1 goes to x to the minus 2, yeah. So I got the right thing here. And then you do it's minus 1 over infinity minus 1 over minus 1. And this is just 0, so it's going to be 1. That's obviously not true. I mean, okay, I think the point is this is something finite. I'm just messing up the integration for whatever reason. This is something finite, so it's not divergent. Yeah, and then the sketch is fine. Like the sketch is just like this. No, not like that. It's like something like this and this, and for 1 over x squared is going to be positive always, so like that. Okay. I don't know what these symbols mean. Okay. Let me ask. I'm gonna ask ChatGPT. Uh, What is sin? Um, oh, it's some like formulas in terms of E, okay. So, okay, so sin X, I'm being told, is e to the X, what was it? E to the X minus e to the minus X over 2. Find the inverse, so you just do it. Um, and then this is quadratic in terms of e to the X, we solve it and you take a learn and then you're not. I think it's the same for the others too, so yeah. Okay, 104. Um, okay, yeah. Sketch the solution to this differential equation. Um, I think we'll come back to this one. This is looking quite difficult. I think this is all the sketches. Let's do this at the end. Um, this one show holds for rational numbers. Okay, so if you have, okay, so the point is, yeah, I think, um, okay, I think this is looking not that bad. Yeah, because it's just like, okay, so if you have P over Q, you can just spam it Q times. So this is a thing Q times, and then this is F of P, which you know because it's an integer, because it's K to the P. Then this thing, because of the equation, is F of P over Q to the Q. So you know that F P over Q is K to the P over Q. Yeah, fine. So we're done with this one. Okay, I'm just gonna remove stuff from the list. So we did, what do we do? We did 116 when we're gonna do 115. We did 108, probably. Yeah. We did 107. We did 81. 71. Oh, okay. I think for this number, let's find the digit sum. So, oh man. Okay. I'm just gonna ask what's the digit sum of this number. I'm not adding that up to life. What is digit sum of this number? Oh, I need to send the number. It is 59. Okay, 59. Um, it looks even though, because you have four ones. Oh no, wait, you have five ones. Yeah, 59. Okay. So there's no multiple of three. Um, what is the sum of the even digits? Like just checking like more different things minus the sum of the odd digits. It's 45. So again, no multiple of 11. Um, wait, how many digits does it have? This is like a terrible question. It has 20 digits. Okay, so the last one is an even digit, and some of the even digits is 52. So, okay, so so the number is 1 mod 11. Squares can be 1 mod 11, fine. Um, yeah, this is actually a terrible question. Okay, it's just gonna be like mod some random number. Like I think, yeah, mod 80 will fine, because 224 is a multiple of 8. mod 9. I mean, it's not multiple of 3. Okay, wait, what is... Because this sum was 59. So it's... Oh, wait, okay, it's 5 mod 9. Okay, the number is 5 mod 9. And squares can't be 5 mod 9, I don't think. Yeah, because 1 squared is 1, 2 squared is 2 is 4, 3 squared is 0. Yeah, because squares can... Wait, so we said it's 5. We're saying it's 5 mod 9, which is 2 mod 3. Yeah, so it's 2 mod 3, so it can't be a square. Fine. Oh, okay, so we did 71. 36. Find, oh my days, find positive integer solutions to this. Um, yeah, I can't lie. What are we doing? I don't know who's saying these questions. Positive integer solutions. It's gonna be like some random mod argument again. Okay, well, 2015 is 2 mod 3. So both of the numbers need to be not multiples of 3. Okay, that doesn't help. Mod 4, what was it mod 4? It's 3 mod 4. Okay, and you can't make sum of two squares 3 mod 4. Because square's gonna be 0, 1 mod 4. Yeah, so square's gonna be 0, 1 mod 4, and 2015 is 3 mod 4. So you can't have a sum of two squares being 3 mod 4, so there's no solutions. Okay, will this have any, oh, again, like some random number, okay. How many digits does this have? Like, yeah. How many digits? It has 9 digits. So the digit sum is 45. So it's a multiple of 9. Okay. Um, so x is a multiple of 3. Okay, so x is a multiple of 3, so x is 3x1. So you have 9x1 squared plus 33y squared is the number. Then you divide by 3. So you get 3x1 squared plus 11y squared is like whatever the number over 3. And then y needs to be a multiple of 3. So you get the t over 3 is multiple of 3, which is fine. So you get the x1 squared plus 33y1 squared is t over 9. And, okay, what's that number from that? I'm not doing this live. What is that number divided by 9? It's a multiple of 5. Okay, it's a multiple of 5. I forgot about that. So mod 5. Mod 5, you got options for squares. Like 0, 1, and 4. So, yeah, you should be fine. I think. Okay, no, for twice the square mod 5. Okay, no, for 3 times the square mod 5, you can have 2 or 3. And for a square mod 5, you can have 0. Okay, 0, 2, or 3. And for a square mod 5, you can have 0, 0, 1, or 4. Okay, so for a square plus 3 times the square to be a multiple of 5, you need to have 0 and 0. So x and y are both multiples of 5. And then like, so the left hand side is multiple of 25, but the right hand side isn't. Yeah, that's it. So there's no solutions again. Like, yeah, I don't see the point of questions like this, to be honest. Like, it's just like you have to, like, it's the same question every time. 34. Sketch this. Okay, we're gonna have to do some sketching at some point soon. This one. Okay, so x squared. Okay, this is pretty easy. X squared is ny squared. So x is y root n, or x is minus y root n. So it's just going to be two lines. One with gradient 1 over root n, um, and the other one with the negative thing. Yeah. Find all natural interest solutions when n is 9. So x squared is 9y squared. So x is 3y because it can't be negative. And if it's 10, then x squared minus 10y squared is 0. So like root 10 is irrational. So there are no, because if there was a solution, then root 10 would be x over y, which is not true because root 10 is irrational. Because I mean, you can compare like v5 or like any prime. Like you can compare v2 and then it just doesn't work. Okay, so we did 34. 28, we didn't do something there. Oh yeah, this one, the recursion thing. So, okay, so we said that Sn should be n, and then we were like, Sn is Sn minus 1 plus the ones where you have n in it. And we want to show that this thing in here is going to be n. Well, okay, so the things with n in it are going to be, okay, well, so okay, so if you add n to a subset, you you multiply the product of that subset. You multiply the product of the reciprocal of that subset by 1 over n. So the thing in here is going to be 1 over n times Sn minus 1 plus 1 over n. And Sn minus 1 is n minus 1, so you're good. So you have n minus 1 over n plus 1 over n, which is, oh, which is not 1. Um, okay, no, but I think, yeah, we accounted for the 1 over n. So actually, yes. So Sn is Sn minus 1 plus 1 over n Sn minus 1 plus 1 over n, which is n, as you want. So you have the base case, you have the inductive step, and then, yeah, so it's always true. Okay, 26. Okay, this is one I didn't really understand. Was, okay, so you have a third and root 2. I'm sure you can just have 2 points like this that are both lattice points with the y coordinate an integer. Um, with a plus c is 2 over 3 and b is fixed. Like, why would this not work? Because that gives you 2 lattice points. Um, okay. Um, oh, wait, no way, because, okay, so if a and c are integers, a plus c can't be 2 over 3, so they're not both lattice points. Okay. Okay, wait, let's say you have 2 lattice points, a, b, and some other lattice points, c, d. Um, and you have, this has equal distance. Um, oh, okay, I think I know what the problem is. So it's the thing that root 2 is irrational. So basically, if you, okay, so the lines through A and B, the line through A, B, and C, D is going to have rational coefficients. And so the perpendicular bisector of these 2 points, that line, is going to have rational coefficients. And then so it's going to be something like ax plus by is c, where a, b, c are all rational. That's the perpendicular bisector. And then you plug x is 1/3. So you have a over 3 plus by is c. So y is going to be something rational, which isn't rational. So it's not, you can't have 2 points. And then for every lattice point, obviously you're going to have a radius which works. So yeah, so we did this question. Yeah, I don't know what we're doing yesterday. Um, two people playing a game. All the values for n where the second player's playing strategy. Okay, I think we just do winning and losing numbers. So if okay, so one, well the second player wins for one because the first player has to remove the last tweet. Yeah, and n equals one. The second player wins. Yeah, what? What was the point of the problem? Like, because n equals one, the first player has to remove the first tweet, and so loses. So obviously there's values for n where the second player has a winning strategy. Yeah, I don't know why I skipped this one. Okay, 24. Oh, this one. Oh, so this is one where you have the grid and you have to find the things. So you're just gonna check chat. Do we have any views? Oh, we have 4 views. Okay. Current viewers probably yeah 0, 5. Uh, okay. So the top right is gonna be losing. Um, yeah. So losing, winning, winning. This is losing. This one is winning because you can put them on this one. So okay, you need to be able to put them on a losing square for someone to be winning. So from here, you can only put it on here, which is winning. So this is losing. From here, you can put it on here or on here. Or we can put it on a losing one, so it's winning. It's also winning. Um, this is losing because you have to put it on one of these two or this one. This is winning because you can put it on this one. Okay, I think like inductively, these are going to be losing. These are winning. These are winning. These are losing. And these are winning. And then that's just it. And then for like general, and you have the same pattern, so you start with the top, with this one being losing, and then you have winning, winning, losing, winning, winning, losing, until you get to the last one. But if the last one is winning, you get the same pattern repeating as you go down. And if the last one is losing, well then, then everything in the next row is going to be winning. Yeah, okay. So if you have a row where this one's losing, then the whole next row is going to be winning, which means this square is going to be losing, and you're going to have the same pattern as the top. So okay, so if this one is m and 3 divides m, then you have this pattern here repeat on the odd rows and all winning on the even rows. And otherwise you just have the same pattern as the top repeat everywhere. Fine. So that's 24 done. 22. Okay. Okay, this is another cookie watch. So I think we're actually doing quite well in terms of speed this time. Um, okay, so if you have R squares, you have 64 choose R for where to put them, and then you have 2 to the 64 minus R for the other squares, and then you're summing this. Oh wait, I think I've seen this question before. I think this is from BMO 1 of one of the years. Yeah, because you do the even sum and you do the odd sum, and basically you realize that it's the binomial expansion of something. Like yeah, it's binomial expansion of 2 minus 1 to 64 when r is even and odd. So yeah, so if you think about it, this is going to be 64 choose 64 times 2 to the 0 minus 64 choose 63 2 to the 1 plus 64 choose 62 2 squared and so on. And these things are the ones with an even number of red counters, and you're subtracting the ones where you have an odd number of red counters. Then this thing is obviously 1. So there's more with an even number of red counters than an odd number of red counters. So yeah, I'd seen the question before, but I forgot how to do it. It seems. 15. Uh, yeah, this is looking kind of difficult. We'll come back to this one as well. 9. Okay. Um, I mean, it feels like it should be something with evens and odds. Um, okay, so you start with A and B, and you go to A minus B. Okay, let's look at some small cases. So for 1 you can, for 1, 2 you can, for 1, 2, 3 I think we couldn't, for 1, 2, 3, 4 we couldn't I think, but for 5 you can. For 6, you you can, because you can go 5, 3, 1 if you take these pairs, and then this goes to 2, 1, which goes to 1. Okay, so I think it's like a mod 4 thing. Um, oh, fine, the sum of the numbers. So when you go A, B to A minus B, basically the parts of the sum stays the same. And then the thing is when n is 1 or 2 mod 4, the sum is even. Oh wait, no, the sum is odd because it's n plus 1 over 2. So when n is even, this is okay, no, sorry. When n is 0 mod 4, this is even. When it's 0 or 3 mod 4, it's even. When it's 1 or 2 mod 4, it's odd. And a thousand is, well, 1,000 is 0 mod 4, so it should be possible. Wait, no, it shouldn't be possible because the sum is even at the start, and mod 2 doesn't change. So the sum at the end can't be odd. Okay. Yeah, I don't know what I was doing yesterday. Um, yeah, we'll come back to this one as well. Um, this one, like, I guess it's kind of a advantage because I've had some time to subconsciously think about the question, and like this is one like I was naturally just thinking about after the stream, and I was like, okay, so if you think about it, you can do it recursively. So if you have, say you have n dimensions, the number of edges in that dimension is gonna be, well, if you think about it, you take to get a cube, you take two squares and then you connect them. So for an n-dimensional hypercube, you're taking two n minus one dimension hypercubes and you're joining them together. So each of those two n minus one dimensional hypercubes are gonna have en minus one edges, and then the stuff joining them together, well, it's in pairs. So you're going to have Vn minus one of those. So we've got a recursion, which we can solve. And like the number of vertices is like obviously, um, well, 2, 4. Yeah, it's obviously 2 to the n. So you can get a recursion for the number of edges and solve it. And the coordinates of a 4D tesseract will just be like, I mean, you just have your four-dimensional coordinates and you just like alternate between 1 and 0 for each thing. So, and what would the longest length be? Well, with Pythagoras in 4D, it would be just this, which is root 4, which is 2. Okay, so that's 5. Uh, okay, so we just need to do literally just the graph sketching ones, and this one, and 15. Okay, let's do 15. Um, okay, so you have, if it's 0 points, you have one region. 1 point, you have one region. 2 points, you have two regions. 3 points, you have. Okay, let's think. Let's think like more clever about this. So you start with one region. Every time you draw a line, you add a new region. But stuff like intersects. So if I add a new thing here, how many new regions do I get? Well, before I had 1, 2, 3, 4, and after I add this, I have 1, 2, 3, 4, 5, 6, 7. So it's a +3. Um, even like, okay, so if I have one, I have two regions, and I add another one, and that increases by 2. So it's like, yeah, I feel like every time two, yeah, okay, so if two segments intersect, you get an additional region. But if they're like parallel, like they don't intersect, you don't get any additional regions. Okay, yeah, that's fine. I think that's fine. Um, yeah, so you start with one region, and for each edge you add one region, and then for every intersection you add another region. I think this logic works. Um, yeah, well, this was something similar before. So, okay, well, when you have an intersection for any quadrilateral is going to give you exactly one intersection, and you have n choose four quads. So quadrilaterals. So that's your answer. Okay. 8. What was 8? Um, yeah. Okay. I think we might have to go to graph sketching. 104. What was that? Oh, this one. Yeah, I think we're doing graph sketching. Okay. Okay. Let's do 115. Um, yeah. So 115. Considering this graph, prove this thing. Well, it's the infinite something. Again, so you can bound it by the integral. So you can say that the integral of 1 to infinity of x to the minus s dx is gonna be this thing. And we're saying s is bigger than 1. Okay, wait, let's draw this graph. Um, we're gonna have to do this at some point anyway. So, I mean, 0 is a point. and it's gonna be something like this, something like that. And if you just sum the integer things, that's gonna be less than the integral. Yeah, it's gonna be less than the integral. So this probably evaluates to s of s minus 1, but I just forgot how to integrate. And then, okay, and then for the other thing is when you show it's bigger than 1 over s minus 1. Okay, but if s is bigger than 1, then s minus 1 is bigger than 0. So 1 over s minus 1 is less than 1. And you have 1 in this. So this is the low bound is obviously true. Okay, so we did 115. Nice. So we just have the graph sketching. Um, this another graph sketching thing, and this weird 3D shape thing. Okay, so let's do the graph sketching, and then we'll come back to these. Hopefully the graph sketching isn't too hard. Okay. Sketch x limits. Okay. Um. Okay. X is 0. Can you do ln 0? You can't. Okay. So x is 0 doesn't exist. So x needs to be bigger than 0. We should probably differentiate it. So you get ln x plus 1. And so as x grows, this derivative will grow. So yeah, so there are no stationary points. Oh no, you have a stationary point at x is e to the 1 over e. Sorry, e to the minus 1. And yeah, so you have a graph. The the derivative increases. Yeah, the derivative increases. So you have this point 1 over e. Um, you have this point 1 over e minus 1 over e. And you start like basically at 0, like around 0. And then you go down here, and then oh no, you can't have x equals 0. What? Okay, this is why I really don't like graph sketching. Okay, so ln of 1 over e is minus 1. And then if you put x is e to the minus 1, you get 1 over e times minus 1, which is minus 1 over e. So that's the point on the curve. But then it increases. So like yeah, as x gets very big, this is gonna get very big. Oh, okay, but at x equals 1, it's equal to 0. Yeah, because ln 1 is 0, so it's gonna be something like this. So it's gonna increase after here, and it's gonna decrease up until here, something like that. Fine. Yeah, that's this problem. Next one. Ln x over x. Okay. So again, just differentiate it, find the minimum point. So it's yeah, what's the quotient rule? Um, like fx over gx. If you differentiate it, it's fx. It's like this. Okay. And then basically, so if you differentiate ln x over x, you're gonna get 1 minus ln x over x squared. So your stationary point is going to be at x equals e, and when x equals e, y is 1 over e. So that's your stationary point. When x is 0, that's illegal. When x is 1, you get 0. And when x is like a half or something, it's going to be negative. Yeah, so it's going to be something like this sort of thing, like this, and then after here the derivative, it's going to be like that. And then solve the equation. Um, well, you can take log. You take ln of both sides. So you have b ln a is a ln b, and you have ln a of a equals ln b over b. So the only solution is a equals b. But that doesn't feel true. Um, yeah, if you take a equals 2, b equals 4, that's not true. Because that's the solution. Okay, so the graph should be the same at 2 and 4. So it should be like, it should go down a bit. Yeah, probably should go down a bit. Wait, but you have no other stationary points, so click on that. Probably goes up and then down and then up. Wait, but there's no other stationary points, so how could that can't happen? Um, okay, so at a equals 2 is ln 2 over 2, and at x equals 4 is 2 ln 2 over 4, which is ln 2 over 2. So it's the same thing. Okay, is ln 2 over 2, and you compare that with 1 over e. Um, 1 over e. Well, okay, so it's ln root 2 or ln 1 over e. So it's e ln root 2 or 1. So it's ln root 2 to the e or ln e. So it's root 2 to the e or e, but e is bigger than 2, so it's smaller. Okay, so the thing should go down after e1 over e. So it should be something like this goes to 1 over e, goes down and then goes up, like something like this. Yeah. Yeah. I think this is like the rough thing. When I'm doing my own interview, I hope they give me good hints for these conversations, because yeah, I'm not very good at it. So sketch y equals x dx. Okay. So differentiator, so it's e to the x ln x. And you differentiate it, then you get ln x, e to the x ln x. And if this is 0, x is 1, is the only possibility. So your only central point is when x is 1, so 1, 1. When x is 0, well, okay, 0 to 0 is like, I think it should be 1, so we'll put 1 here. And okay, can that thing be 0? No. So it's something like, okay, and the derivative between 0 and 1 is, I mean, it's always going to be positive, right? So it's always increasing. So it just like kind of increases. And the rate of increase increases. So it's going to be like very sharp. And x to the 1 over x, well, that is x to the ln x over x. So you differentiate it and you get, sorry, e to the ln x over x. So you differentiate it and you get Again, you have to differentiate ln x over x, which we did somewhere. And we got 1 minus ln x over x squared. And, okay, so this is 0 when x is e. Yes, you have a turning point at x equals e. So you have e and e to the 1 over e. As a turning point. And then, wait, I'm gonna just double check my math's been working, just in case. Actually, no, wait, the thing is showing, so we're fine. Yeah. Okay. Yeah, integration is, no, not integration, graph sketching is not it. And then, like, can y be 0? No. Okay, if x is 0, I don't know. Okay, if x is very close to 0, what happens? One of x is very big, so it's still gonna be very close to 0. Yeah, and then if x is like infinity, then it's gonna be again very close. So it's gonna be something like this. It's go up, then it's gonna go down, and yeah. And then for the negative ones, wait, we didn't include negative numbers. I mean, yeah. I mean, for negative x to dx is like kind of weird because like obviously you can't have minus half to minus a half because you can't square root something negative. So it kind of continues a similar thing. Like I'm not gonna draw it. So yeah, I mean, okay, for this one, if you go to infinity, this should go to 0, and then if you go to minus infinity, it should also go to 0. I'm thinking, um, because yeah, because 1 over x gets very close to 0, and then yeah, so again, it will go like close to 0, something like this. It's fine. Oh, okay, sin x over x. Um, I mean, when x is very small, sin x is basically x, so it's gonna be 1. At x is 0, it's undefined. If it's very close to 0, then it's kind of like an asymptote. Not really. Um, yeah. Okay, so you have roots at like multiples of say pi. Okay, so I'm thinking it's gonna be like this. It's gonna be okay. So when x gets very large, it's gonna be 0 because sin x is still gonna be between 0 and 1, between minus 1 and 1, and x is gonna be very big, so it's basically gonna be 0. So it's gonna be like it's gonna start out. Eventually, it's gonna go something like this. It's gonna oscillate, and then the oscillations keep getting bigger, and the zero is just gonna go up, and then same thing on this side, but it's gonna come from below and keep oscillating until you get very small. And for this one, um, again, it's a similar thing, but you have the asymptote at 1, and it's like the same thing when you oscillate and you go to 0, and from here you oscillate and you go to 0. Yeah. Um, 87, cos 1 over x, sin 1 over x. Um, yeah, I've done this like a billion times. Basically, the idea you have a lot of roots between 1 and you have a lot of roots between 1 and 0, but then after that you have no roots. So you have like a bunch of roots here. At 0 it's going to be undefined, really. So you're going to have a bunch of roots here, and then the oscillations are going to become much smaller. So like similar to that thing, I guess. And it's the same for sine 1 over x. Like, yeah. I think the idea is clear for these. Okay, 88. Um, so this is gonna tend to 1 as x gets very big. And close to 0. Yeah, so like y equals 1 is a is an asymptote type thing. Um, and then okay, so when x is very small, x minus sine x is very small, so the thing's gonna be very big. So it's kind of like it's gonna be very big here, and it's gonna be very small here, and actually it should come from above because the x equals, you can't have it being negative, I don't think. Um, you know what? Okay, yeah, we've been going for a while. Um, okay, we could like differentiate and find turning points again, but I think okay. So when it goes to infinity, it's gonna be very close to 1. When it goes to minus infinity, it's gonna be very close to 1. And then when it's close to 0, it's kind of like an asymptote. Yeah, yeah, I can see why nobody else has tried to do this sort of live solve because like some of the questions are actually quite difficult to do live. But yeah, it's still good practice to do them under conditions like this. So yeah, um, yeah. So when x is close to 0, it's gonna be very big, and then can it be equal to 1? Yeah, whenever sine x has a root, it's gonna be equal to 1. So it's gonna oscillate around 1. So it's gonna have infinite roots at 1. Yeah, it's something like this. Okay, yeah, I'm just gonna take that off. Okay, next one. Okay, so if x is negative, then that's just called 0, which is 1. Okay, so if it's negative, it's just gonna be 1, and if it's positive, it's gonna be close to 2x, which is very easy to plot. Um, so you're gonna have at pi or even a pi over 4, it's gonna be 0. Yeah, so it's just gonna be like a drunk version, like what's it called? Like a stretch but factor of half. Okay, yeah, I think this is the easiest graph sketching one so far. Okay, sketch this. Okay, so let's sketch x cubed minus x. So you have 0, 1 minus 1 as roots. So you have something like this. And if you square root it, well, it's gonna be undefined when it's negative. But when it's positive, it's gonna be still 0. This can be something. It's gonna be a similar shape. It's gonna be like something like this. And then from here it's gonna be something like the same thing. And then for y squared is that, well, then you can just flip this thing over. So I mean the right side still has to be positive, but you can just flip this over and you can flip this over. And then that's the y squared thing. Okay. Now sketch. sketch this thing. Okay, so does it factorize? Yeah, it factorizes as x squared minus 3, x squared minus 4 over x squared minus 2 all squared. So root 2 and minus root 2 are the asymptotes. And you have like a bunch of roots. So you have roots at 2, minus 2, root 3, minus root 3. And it's gonna, as x goes to infinity, it's gonna approach 1. Because yeah, it's gonna be the same thing. Because I mean the leading coefficients of the top and bottom are the same thing. So and at 0 is gonna be 3. And it's even function because it's all the mass is x squared. So and do we get 1 ever? Well, we get 1 if this thing's true. Um yes, you get 1 at like square root 8 over 3. Um which is okay, so yeah, so you hit 1 as you go down here. So you go up and then you approach 1. You never hit 1. And it's gonna be the same on the other side. Okay, sketch 92, sketch this thing. Okay, so you never get y equals 0. The asymptotes are 1 and minus 1. Again, it's an even function, so I'll just do the right side. When x is 0, you get minus 1. And when you can never have y 0, we're saying. So it's gonna do this. And then for this one, it's gonna be something like this. Oh, no, and it tends to 1. Yeah, as it goes to infinity, it tends to 1, not to 0. So yeah, that's something like this. Yeah. Okay. Okay, we're not even almost done. There's like 2 more on these days. Um, yeah, sketch that thing. Um, so again, it's even, so I'll just do the right half. So, okay, so if x is bigger than 1, it's gonna be x to the minus 1. And that's just, and at 1 it's gonna be 0, so it's just gonna be the, like, quadratic. And if it's less than 1, it's gonna be 1 minus x squared. So it's gonna be like a negative quadratic. So like this sort of thing, like that, onto 1. And the derivative, well, it's going to be the derivative of 1 minus x squared in this region, and the derivative of this in this region. So it's going to be minus 2x here, and 2x here. Okay. For 1 over 3, x to the 1 over 3, well, it's going to be basically like root x, which I think is something like this. Um, yeah, something like that. And the derivative is a third x to the minus 2 over 3. And the squared version, well, you just square it, you know. Yeah, okay, so it would be something like it would go down as well for the negative bit, but then when you square it, this thing will go up here. And the derivative is like whatever it is, like two over 3x to the minus 1 over 3. Yeah. Okay. 94. Um yeah, sketch that. Okay, this is not too hard. So you have roots at 0, 1, minus 1, so it's x squared, 1 minus x, 1 plus x. And basically like it's just a normal quartic. So you have minus 1, 0, 1. It's gonna be something like this. It's gonna just like that. Like this. Yeah. And if you square root this, well, these regions are illegal, so it's gonna be like a dot here, It's going to look like this. It's going to go, you can have the negative version as well. And it's going to be like this and then like this. Okay. And the derivative at the origin carefully. Bro, I don't know. Okay, dy by dx. What's dy by dx? Well, it's because if you do d by dx, you'll get 2x minus 4x cubed is 2y dy by dx. So dy by dx is x minus 2x cubed over y. And at x equals 0, or y is also 0. So the derivative is undefined. I mean, because there's no other points around it, so it's called undefined. Okay. Sketch this. Oh my. Okay, differentiated. Oh, days. Minus 2x e to the minus x squared plus 6x e to the minus 3x squared. Yeah, when is this 0? It's 0 when so divide by 2x, so you get e to the minus x squared plus 3 e to the minus 3x squared, and then and these two equal, and this is this thing cubed. So you just do this. So e to the minus x squared is 1 over 3. So e to the minus x squared has to be root a third because it's going to be positive. So you take the ln, so minus x squared is ln of 1 over 3 to the half. And yeah, I can't lie. This is so bad. Okay, so it's gonna be some point which is less than 1. Again, it's an even function, so I'll just do the right side. Um, and it's okay, so it's a third minus a root third cubed. So it's a third root third. So it's 2/3 root third. So that's the turning point, and it's gonna be a maximum because it's kind of like t minus t cubed if t is e to the minus x squared. So it's gonna tend to 0. No, it's gonna go negative, right? As does t get very big as x gets big, t gets small because minus x squared gets small. So they're gonna get closer together. It is gonna tend to 0, yeah. But okay, at x equals 0, it's gonna be 0. Then it's gonna go up to here, then it's gonna down to that, and then same on the other side. Yeah. Okay. By sketching appropriate. Oh my. Okay, fine. Sketch this graph. So we're sketching. We want to sketch x minus 1 over ln x, and then find when that's equal to e minus 1. Well, at x equals 1, it's gonna be 0. At x equals 0, it's not defined, but it's gonna be negative. It's gonna be negative, so it's gonna be something like this. And then as x gets big, x is gonna be bigger than ln x, so it's gonna grow. It's gonna be like this. So there's only gonna be one solution, and can we guess a solution? Like x equals e. Yeah, x equals e is calm. Yeah, so basically, it's we say that there's no there's no point where it doesn't cross over itself, and x equals e is a solution, so there's no other solution. Yeah. So sketch the graph. I don't. Yeah. Graph sketching's gotta be the worst topic in maths. Yeah. Okay, so again, differentiator, it says hence, but I can't see how to use first part and second part. Like, yeah, I can't see how to use the first bit and the second bit. So, okay, no, if I say it's y minus one instead, then I can rearrange for ln x and do something. Like, ln x is x minus one over y minus one raised to the power of e, so x is this thing. And you can times by e to the y minus one on both sides, so x e to the y minus one is e to x minus one. Um, yeah, I can't like this is like so bad. Okay, so let's differentiate and set to zero and find the turning points for the like 10,000th time. Um, yeah. So when is this gonna be zero? Okay, maybe this is where you use the first part. Yeah, I think this is. You have to get e to the x minus one. Is okay, yeah, we're back. Okay, look, I need to get some sleep. So yes, we got the turning point. X equals e and the function zero. So at x equals zero, the function is one. And so it goes like this, and then it's gonna grow like that. Yeah. Okay, 97. This is so bad. It's like, um, okay. So write this in this form. So y equals 3 e to the x minus e to the minus x with e to the x plus e to the minus x. Well, this is, you write it in some form. Times one bottom by e to the x, so 3 e to the 2x minus 1 of e to the 2x plus 1, which is 3 e to the 2x plus 1 minus 4 of e to the 2x plus 1, which is 3 minus 4 of e to the 2x plus 1. Yeah, okay. And then basically it's gonna approach 3. Like that's the main thing. And as x is very big, it's gonna tend to 3. When is it equal to 3? When this is equal to 0? Well, it's never equal to 0. So it's always gonna be a bit below. Okay, when x equals 0, this is 1. So it's gonna be like this. Like getting close to 3 but never reaching 3. And on the other side, it's gonna be the same thing though. Yeah. Oh no, but on the other side, it's gonna no, no on the other side it's gonna tend to this thing is gonna tend to 4 over 1, so it's gonna tend to minus 1. So when you plug x as 0, you get minus 1. Wait. When you plug x as 0, you get 1. As x tends to minus infinity, this thing vanishes, so you go to minus 1. Okay, so when is this thing 0? Well, when 4 over e to the 2x plus 1 equals 3. Oh my days, this is so bad. This is like, so e to the 2x plus 1 is 4 over 3. So e to the 2x is 1 over 3. So x is like, so 2x is like ln 1 over 3. So x is a half ln 1 over 3. which is like minus a half, and then 3. So you have like some point here, and then it turns to 7. Okay, sketch this thing. Um, yeah, so n equals 2, x to the 4 plus y to the 4 is 1. So it's like a circle type thing. So it's like, so you have 1, 1, 1, 1, minus 1s. And then like, it's gonna kind of be like a circle, but it's gonna be, it's gonna be more, I don't know, man. It's gonna be like the square root graph, I think. Yeah, it's gonna be more oval-like. It's gonna be oval-like with the top being thinner. That's what's gonna be. Yeah, it's gonna be like an oval with the top being thinner. Yeah, and then for 8, it's a similar thing, but it's gonna be more. It's gonna get closer and closer. So as n goes to infinity, this is gonna get closer and closer to a square. Yeah. Okay, and that was actually the next question. Okay, sketch the curve, whatever. Um, on my base. Okay, so either 3x squared plus y squared minus 12 equals x squared minus y squared plus 4. So 2x squared plus 2y squared is 16, so that's just a circle. So you got a circle since 0, or you have is, and you get rid of y squared, so 4x squared is something is 8, so x is root 2. So x is some constant. Fine. Okay, this was a very easy one. 100 sketch this thing. Getting to the end. Um, I mean it's an even function again, so I'm just gonna do the right half. And okay, so you have okay, so again you can differentiate, find the turning point, and do that all that stuff. I I don't have the mental energy to do that right now. So we're gonna see what happens at x equals 0 when x goes to infinity. So okay, can y equal 0? No. Y can never be 0. When there's gonna be some turning point here when it goes down and goes up. And then as x goes to, I mean, no, x has to be, yeah, x has to be less than 1 anyway. So when x equals 1, you're gonna get, you get root 3. Yeah, so x equals 1, you have root 3. So it's gonna go down at some point, you have a minimum, it goes up, then you get root 3. And the same on the other side. There's gonna be some minimum point, which is your turning point, which is whatever the turning point is. And then 101, sketch that. Well, it's just a square. Like, it's just a square like this. Um, for this thing, mod y is mod x minus 1. So, okay, so y is mod x minus 1, or y is 1 minus mod x. So, if x is, so if mod x is bigger than 1, this one's true. If mod x is less than 1, this one's true. Oh my days. Okay, so if mod x, okay, so if x is bigger than 1, okay, so x is bigger than 1, then it's going to be x minus 1, so it's going to be like this. If x is between 0 and 1, you're in this case, so we're going to have 1 minus x, so it's going to be like this, and it's like, it's going to be like, yeah, at x equals 0, x equals 0 is impossible. Okay, so it's going to be something like this. But no, y can't be positive in this case. But no, in this case, mod x is 1 minus y, so y can't be bigger than 1. Yeah, okay, so it's gonna go like this until you hit 1 where it's not defined. Yeah. Actually, wait. Okay, mod y is mod x minus 1. Okay, so actually, no. Yeah, so mod x is always bigger than 1. So you're either gonna have this, or you're gonna have, and on this side, you're gonna have minus 1. As your thing is gonna continue like that. Okay, and it's the thing, well, that's just a circle. That is just a circle. Something. It's like y minus x is 1, or y minus x is minus 1. And so y is x plus 1, or y is x minus 1. And it's just those two lines. So we're done with this. What's the area of the region in this plane where this is true? Well, um, well, it's always bigger than 0. Because if y is 0, it's mod x is 2 mod x less than 2, so mod x is less than 1. So, okay, so y equals 0. Y equals 0, mod x has to be less than 1. Similarly, if x equals 0, y, mod y is less than 1. So you're bounded here. And then, okay, so x equals y equals to half doesn't work. Um, I don't think I know how to do this one. Yeah, I'm stuck on this one. I don't know what to do. Should I ask chat? Should I ask chat GPT? No. Yeah, we don't really have a chat. We don't have views. It is quite late to be fair. Um, yeah, so I'm gonna ask, AI how to do this one because I don't know what to do. Oh, it's literally just cases. Yeah, it's literally just cases. Oh my days. Okay. Yeah, my brain's just fried. Okay, so you literally just do cases if x is, if they're both positive or both negative, you just do cases. So if they're both positive, you have x plus y is less than 2. So x plus y is less than 1. That gives you a triangle. You get there of that, and then let's say x is bigger than 0, y is less than 0. You have x minus y plus mod x plus y is less than 2. And then wait, what was it saying? Then it's saying that, oh yeah, it's either going to be x minus x minus y, which is minus 2y, but y is less, yeah, it's either going to be It's going to be 2 times the maximum. I'm reading this off the AI script. It's going to be twice the maximum of mod x and mod y. And that's, so the maximum of mod x and mod y is less than 1. So you have 2 cases, each case gives you area 1. So the total area is 3. Fine. Okay, so yeah, we couldn't, like, we could have done this, but like, yeah, it's way too late. Way too late to think properly. And yeah, I have to say the stream has not been very enjoyable. Yeah, it's just been suffering. Like, I think like yesterday was kind of fun at points, but today it's just been suffering. It's just pure suffering. Um, yeah. Okay. So okay. Yeah. So when yeah, I don't know how to sketch the solution for this. Yeah, I'm just gonna sketch for this one as well. Like, yeah, just pure suffering. Whether there's a typo in this thing, I think. Yeah, no, okay. Uh, Oh, so then you just do cases. Yeah, so I mean, yeah, you can read this. So yeah, yeah. I mean, yeah, this is stuff that I don't know how to do. To be honest. And I think that's everything. Yeah, we did 115, and the only one left of this is this one. I had an idea for this one while working on a different question. So my idea is like you you look at the angle here, theta, and you can write if this is m and this is n and this is theta. I can write this distance as n over cos theta, and this distance as m over sine theta. So your total distance is m over sine theta plus n over cos theta. And then I'm feeling like you need to maximize it. Because again, you differentiate with respect to theta, set it to 0, find the optimal angle, plug that back in, and that gives you your distance. And this doesn't work. Should we do it? I mean, it's the last question, so let's do it. Just to check, it's definitely whether you got the right trig function. Um, yeah, I think, yeah, I've got the right function. Yeah. So you have m over sine theta plus n over cos theta. Differentiate this. So 1 over sine, okay, what does 1 over sine differentiate to? It's going to go to -1 sine theta to the -2 times cos theta. And cos theta to the -1 is going to go to -1 cos theta to the -2 times minus sine theta. So it's going to be sine theta cos theta to the -2. So you're going to get m times this was going to get minus m cos theta over sine squared theta plus um, n sine theta over cos squared theta. And these things to be equal. So, and basically, we need to find theta. So, multiplying across, you get m cos cubed theta is n sine cubed theta. So you get the m over n is tan cubed theta. So tan theta is the cube root of m over n. And yeah, theta is the tan inverse of the cube root of n. And there's some like formula for sine in terms of tan. So like sine squared theta plus cos squared theta is 1. So tan squared theta plus 1 is 1 over sine squared theta. So you can calculate, okay, we can actually calculate this and plug it in. Yeah, let's do it. So you have the cube root m squared over n squared plus 1 is 1 over sine squared theta. So 1 over sine theta is going to be square root of this. So it's going to be the square root of the cube root n squared over n squared plus 1. That's 1 over sine theta. So m times this. That's your m sine theta. M over sine theta. And the n cos theta thing is going to be like n square root cube root or reciprocal of this thing plus 1. And yeah, I think that's fine. And that's all 151 questions. It's taken around 5 hours. Yeah. But at least we got it done in 2 days. Like I've heard some people take like 2, 3 months to do this booklet, so at least I got the whole thing done in 2 days. I don't need to think about this booklet anymore. Like maybe I'll go over the graph sketching ones in more detail because I didn't really go through the details in a lot of them. But I think at least I have a good idea of the difficulty of these interview questions, and I practiced doing them on the like on the more intense conditions than just doing it on a paper at home. And hopefully, it's something that you guys found useful as well. So yeah, that's it. And yeah, I don't think I have any views, but